Thank you very much, everyone. I hope you all have a wonderful day today. So let us start today's session. So we have a very excellent speaker. I think Dr. Utkarsh Mishra, have you joined, sir?
Yeah, hello, ma'am.
Okay, hello, sir. Okay. So let's start our session. First, introduce our speaker to our participant. Uh, Dr. Utkarsh Mishra is an assistant professor in the Department of Physics and Astrophysics at the University of Delhi. He earned his PhD degree from Harish Chandra Research Institute in 2016, where his research focused on the dynamics of quantum correlation. He had a postdoctoral position at the University of South California, Los Angeles, the University of Electronic Science and Technology of China, and the Asia Pacific Center for Theoretical Physics. South Korea, he was also in South Korea from 2016 to 2018. His research interests include quantum metrology, entanglement dynamics, and quantum phase transition. Welcome you, sir. I think sir have a wonderful, theoretical and theoretical and experimental exposure of quantum metrology, quantum correlations. So let us welcome Hur Harley, sir. So welcome you to the Quantum Technology for Innovation and Startup, our course. Over to you, sir.
Thank you very much, Professor. I'm on the sheet. I don't know what.
No, it will come. It is coming, I think.
It's coming.
It's not
Visible.
still not visible. Or if you do share, there is a two option: screen and window, right?
I have next button. There is a share.
Yes. If you share, then there is an option is screen or window. Just share. You click on share, then there is a two option: screen or window.
Click on the window.
Yes, and now open it with auto.
So
You must open your PPT on Windows. I think now you have, so team is visible.
and now this is my.
Just only open your PPT.
Then I've shared. I cannot click on the presentation content only.
Oh, there is a screen window. There is, yes, better. So it is like keep your that somebody is talking and it's a lot of disturbance. Some background music is coming. Somebody on bike and some road is. This is not good. So it's my humble request. Please mute your mic.
Is my screen or anything visible now?
No, sir. I think no, it's not visible. Again, sir, if there is an issue, you can share it with us. I can just flip on that is also possible.
Okay. So because I think I have a team. Yeah, I have Microsoft Team, and I clicked on that, and then I click on the share.
Yes.
Then there's a window, but I cannot then do anything else over there.
I think maybe you have an old version, because if you do on a share, it will come as a content and then a screen and window, and you look on window. Or simply, sir, you can mail us your PPT. My student will simply.
Okay, I can.
This is also an option.
So you have, okay, let me, so this is camera is here, mic is here, and then the share, right?
Share, yes.
So I click on the share, and then so once I click, there's a presenter mode.
Yes. So, and then below there is a screen and window through option.
Yeah, so when I click on the window, I cannot click
just
there.
then if you're no, if you click on window, then there is a three option is come. There's a some option will come if you click on window. Like a double click maybe.
Yeah, I did double click.
Or you simply you can share about your PPT with us. Or my student will like you can just say next and he will move the there is no issue. So yes, you're audible, Divanshu.
Ma'am, is it possible? Because I'm trying to click on a window, but still I am not able to do that.
Oh, sir, please, you can just mail me on
Okay, I'll
WhatsApp
just.
me, just PPT, we will share with you. Don't worry. Just WhatsApp me your PPT. That's WhatsApp is a PPT or mail me anyway. We will
Yeah, and I
do
am
that.
trying to send an email.
Mhm.
So does it, the link that you share is also working on the team app? If I just go to team
Yes,
app.
yes, 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 yes. Because I am open a team app. Suppose I am like I can show you just how I am sharing. This is my window and I have opened a new tab. And now I think all the participant can see my new tab, right? Right? Dr. Mishra, can you see my new tab?
Sorry, ma'am, you have sent me the meeting link. Do you have meeting ID and passcode? I think you are muted.
We have, sir, a meeting link and password. I'm just sharing with you. Okay.
Okay, ma'am.
Just, I think you need maybe just a minute. Divyanshu, can you share where it is? I think it is with should be permissions. Just a minute. Okay, just. Sir, please, the meeting ID can you please note down? It's a 9388. If you have to put somewhere, you can put it 9388.
Just a minute, ma'am.
Okay.
Yeah, meeting ID
93
93
80
80
81
81
36
36
52
52
550.
00. And ma'am, passcode
Passcode is 8.
8.
Yes, 8 capital H. It's
Capital
already in
H,
chat box. Yes. Small a
small a,
9
9.
E
Ma'am, small or capital?
9 E small
E.
capital W. We have put it in chat box also. Just you can see it.
Oh, okay, ma'am. I think it worked, but
Yeah.
yeah, I think as you mentioned earlier, it's something uh, related to software update, I guess. So
Yes,
I don't
that's
think this is the right time to update. So I have emailed you the my slides.
okay. I'm just checking. I am just yes. Okay. Your mail. Yes. I got your mail. I'm just sending to Devanshu.
I think you also have to give me permission maybe to share my screen.
No, not required. But
Because it says go to security and privacy screen recording.
okay, Devanshu.
Okay, I think it should work. Yeah, ma'am, I think it should work now. I am so sorry.
Coming. Now I can see your on screen. Your meeting ID is open. Yes, now it is coming, sir. Thank you.
My slide is open, ma'am.
Yes, it is open, sir.
Okay, I'm sorry for this technical glitch. I
No,
didn't
it's fine.
open Team for a long time.
Okay.
So I'd like to start by thanking Professor Divya Somansi for giving me this opportunity to present our work. Hi, I'm Utkarsh, and I'm currently an assistant professor at the University of Delhi, and I'm working at the interface of quantum information theory and quantum computing. And for last 3, 4 years, I have been working on quantum metrology and its various applications. So quantum metrology is about the estimating a known parameter. So am I audible to everyone? Just give me a thumbs up.
Yes, sir. You're audible.
Thank you. So quantum metrology is about estimating or determining or measuring a known parameter with very high precision. So that unknown parameter could be the magnetic field, or could be electric field, or could be gravitational field as well. So this branch deal with the parameter estimation, and this estimation parameter could be, as I mentioned, it could be magnetic field, electric field, or the gravitational field. So I will mention what are these parameters are, and why do we need to determine this parameter with very high precision. So I'm going to start by a quote from Professor Chris Ferre, who says that parameter estimation is a fundamental task in metrology, and it is a science of measurement. So there is a science in the measurement. Okay, so we have to use the laws of physics or laws of quantum mechanics when we perform measurement. And the ultimate limit of precision in this task are determined by the laws of physics. So we always ask that how precisely we can measure certain things. And to answer this kind of question, we have to determine, we have to use the laws of physics. And we know that currently quantum theory is something that explain a lot of things that are not possible in the not even class explained by the classical physics. So for example, wave particle duality, from the early 19th century, then the black body radiation, and so on. These phenomena are not explained by classical theory. So therefore, we have a quantum theory which supersedes the classical theory. So we can also ask the question, can quantum theory provide an ultimate limit of precision that overcome the classical theory limit? So this is what we are going to see in this talk, that we have two limits. One is provided by the classical theory, Newton's law and so on, and other is provided by quantum theory like Schrodinger equation and so on. And what is that ultimate limit of precision? We will see in this talk. So let's start with some basic understanding what we mean by measurement and precision and accuracy. So for example, if you have a 100-gram block and you want to measure it, so you'll put in a machine and it will give you some measurement result. So for example, if it is 100 gram, it will give you 100.00 gram is reading. So that is an accurate measurement because the weight of this block is 100 gram. Are there any questions?
No, sir. There is some
Okay.
mic disturbance. You continue, please.
Okay. Now, certainly in the right-hand side, we have inaccurate measurement because the reading is different from the actual reading. So the goal certainly here is that we try to design a machine or measurement operators which give us the accurate reading of the actual object that we want to measure. Now, suppose I add in this 100 gram another mass of value 0.001. Now, whether this addition will be sensitive to this reading or not. Now, because this machine can only give me significant digit up to the second decimal places, if I add a mass in this 100 gram by an amount of 0.001, it will not remain sensitive. It will not give me any reading. It will not deflect. The meter will not deflect. So therefore, to go below third digit in this case, we have to devise a machine which is sensitive to that change in the digit. I mean, that should be sensitive to that mass change, you can say. So it should be sensitive to the third decimal digit change in the mass, then only this reading will deflect. So what quantum mechanics tells us that because the quantum wave function or the very nature of quantum mechanics is very fragile to any small perturbation. That is the very definition of quantum mechanics, that it is very, very fragile to even in the smallest change. And therefore, therefore, even in other talks, we have seen that we want to avoid our quantum system to interact with the environment, because the moment it will interact with the environment, it will lose its quantumness. Okay, that's decoherence. But here we are using that property that the quantum system is very fragile. Even the smallest change in the environment, we can use the quantum system, read it, and determine the environment itself. And that is the entire theory of quantum metrology is. So the measurement has a history that when there was no standard unit of measurement, people were using different units of measurement for length, for mass, for time, and so on. And as the industry and trade expanded across the world, there has been a need to dire for a single standardized system of measurement. And therefore, if let's say economy has to flourish and we need to exchange good and trades between different countries, we have to have a common measurement standard. And therefore, the world has realized it over the time, and they have developed more and more sophisticated tools for measurement. For example, uh, the measurement of length, for example, were earlier used foot, hand, steps, and now they are using more sophisticated devices like vernier calipers, microscope, laser, and so on. So these are the more sophisticated devices that measure more precisely or more accurately the length. And this, over the time, improvement on our measurement capabilities has improved our daily life. So this is sort of important that we have to have a measurement strategy which is more and more and more accurate. And then we can use this tactic for various applications. For example, we can use these tactics for safety and performance. So in the industries like aerospace and medical devices, they are very highly, they have very high level precision, and therefore they are working very functioning very correctly. They will diagnose your treatment, they will detect the cancer and so on, right? I mean, if they are not functioning properly, then they will not detect. I mean, if even if I have a cancer, they will not detect because they are not as accurate. So therefore we have to have these very accurately and detectable devices so that it can be used for medical industry, for example. In manufacturing industry, these precision measurement are a cornerstone of lean manufacturing, and they ensure that the parts are produced in first time and we do not waste the material in trial and so on. In scientific advancement, for example, this precision measurement is very important because it will validate the scientific theories. So whatever scientific theory you have, for example, gravitational theories, that we have a gravitational wave, but we have to detect this in an experiment, and it is so small that so far we were not able to do that. Only recently, 2019, we all know that we there was a Nobel Prize given to the people who designed the instrument that detects the gravitational waves. And now we know that the Einstein theory of gravity, GTR, is sort of explaining the gravity. So for scientific advancement also, we these high precision measurements are very, very, very important. And yet in our daily technology, in modern life relies on it, for example, GPS, cell phones, computers, and they suddenly cannot function properly without precise time and frequency measurement. Also, cost control and efficiency, so precise measurement ensure proper resource allocation in construction and engineering, preventing unnecessary labor and material costs. So this precise measurement has sort of these kind of applications. Okay, so in this talk, I will give what quantum mechanics bring on the table. And as probably you have heard about qubit in the talk, in earlier talks. So how can we use a qubit as a quantum sensor? And then if we add more qubits, then can we get what is called the quantum advantage? And then what are the application of qubit as a quantum sensor? Or if we have a more qubits, then what are the application of those system as a quantum sensor? So there are several devices that one can make using quantum mechanics. For example, one can make atomic clock, quantum magnetometer, quantum gravimeter, quantum inertial sensors, quantum electrometers, and photon detector. So we understand that in all these cases, these devices are somewhere using the quantum property. And what are the quantum property? That the system is represented by a wave function. And if we want to extract anything from the system, we have to perform a complete set of measurements. And if we have to evolve the system, we have to use Schrodinger equation. So these are the three principles that are being used in all these devices. So for example, what does atomic clocks do? So we use our, so we keep timing that what is the time now in India, and let's say somebody asks what is the time in other countries, right? So, but they may have a different, the clocks may have a different time measurement, right? But we want a universal time measurement. We want to have a time measurement which is not different depending upon the country's location. We have to have a universal clock. So atomic clocks are the clocks which are most accurate timekeeping devices ever created. So they can read a fraction of seconds. So how many fraction of second they can read? They can read this fraction of the second they can read. So a second, these atomic clocks can divide a second into these many fractions, and they can read each fraction. So they are sort of so far, atomic clocks are the most accurate timekeeping devices. And for example, they are the atomic clock that, for example, we have in IISER Pune by Professor Umakant Rao Pal, who has sort of tracked and atom, cesium atom, and whose vibrations are measured so accurately. And people know that when there are two-level atom, that they have two levels, then they go from one level to another level, and they keep doing this. And for cesium atom, the vibration of these two levels between the transition between these two levels in 1 second happen these many times. So what they have done in this lab, they have sort of trapped a light of the corresponding wavelength, which give us the so-called the atomic clock. So they can be sort of in a very sophisticated environment, in a very sophisticated controlled manner, they can be created in the lab, the atomic clocks. Now, the other application is quantum magnetometer. So quantum magnetometer measures the magnetic field. So what is the smallest magnetic field that you can think of? So for example, we have Earth magnetic field. And then we have magnetic field in our neurons. Then we have magnetic fields coming from the cells. And one example of the small magnetic field is the MRI that we do in our medical field. So this tiny magnetic field, to detect this tiny magnetic field, is become more and more important. And therefore, we need to have a more sophisticated devices. So quantum magnetometer does that job. So quantum magnetometer measures the magnetic field with very high precision, and they can detect very tiny change in magnetic field with several order of magnitude smaller than the classical magnetometer. So now you can see the advantage of quantum mechanics, that if we can use quantum mechanics and we develop what is called the quantum magnetometer, they can certainly be better than the existing classical magnetometer. So in IT Bombay, for example, they have uh, these kind of devices in the laboratory which can detect magnetic field up to order of picotesla to femtesla. So this is in the lab of Professor Kasturi Shaha, and he is our honorable minister who has visited the lab. The next example is quantum gravimeter. So G, we all know that we have a gravitational acceleration whose values we tell sometime 10 meter per second square or 9.8 meter per second square, depending upon convenience. But that is not the case, of course. I mean, the value of G changes as we go to the height, the value of G changes as we go to the deeper to the earth, the value of G changes. And the change in G is responsible for many phenomena. For example, seismic activities or the presence of oil or presence of minerals can be detected by the measurement of this accurate measurement of G. So this gravimeter, they use the atomic interferometer. So we know that light interferes when we send the light to an interferometric setup. The light interferes and give us the maximum and minimum of the intensity. In a similar fashion, if you drop the collection of atoms in this figure, for example, due to the gravity, they interfere, and those interference are very much dependent upon the change in the G. Therefore, you can measure the G by just the interference pattern there. So people use this kind of sophisticated uh, technique to measure the G up change in the gravitational constant up to the order of 10 to the power minus 9. Just very, very, very tiny amount of change that they are able to measure. And again, they use quantum interference. So the very fundamental phenomena is being used to measure these sophisticated, parameters. The quantum inertial sensor, so these consist of quantum acceleratometers and quantum gyroscope, which measure the change in the linear acceleration and rotation using the principle of quantum interference. So again, the navigation, for example, if you are doing navigation, uh, you one has to have a very right direction, and sort of this kind of thing can be used using what is called the quantum inertial sensors. Quantum electrometers, they measure electric fields such as the radio frequency wave used by effectively all modern communication devices. They are expected to have much higher sensitivity than the classical electrometers. So these are other devices that people use. Photon detectors. You might have heard in earlier talks in this session, in this workshop, that people are now developing devices which can detect a single photon. Usually we have a devices which can detect light. So if light is coming, you have a current, and if his light is not coming, you don't have any current, for example. So the photocurrent devices are there. But single photon detector is very, very crucial for a lot of current technologies that use quantum technologies. And so this is something that people are still working on for to make a more and more efficient, because if single photon is coming, the signal will be very, very small. So you have to enhance the signal somehow. So you have to have a lot of electronics to perform there. So this can be detect individual packets of light called photons. This, for instance, can enable three-dimensional imaging. So these single photon detectors can be used for what is called the imaging. And also the time it takes a photon to travel between object and detector can be sort of calculated by the single photon detector. So for example, IT Delhi has this kind of devices for quantum cryptographic protocols. So the next question is that if I have to make a quantum sensors which can measure gravity, electric field, time, acceleration, and magnetic field, what are the setup I have to use? Where do I sort of make these devices? So as I mentioned that for electric field, what is called the Rydberg atoms, they are very sensitive to the small electric field change. One uses the Rydberg atoms for electric field detection. For timekeeping, of course, one uses atomic clocks, which, for example, I have shown in the previous slide was the cesium atom. Then for acceleration and rotation, we use again atomic interferometer. For magnetic field, there are different devices like atomic magnetometer and what is called the NV center in diamond. So nitrogen vacancy center in diamond. This is very, very sensitive setup for even a tiny magnetic field, which can again sense magnetic field in the range of picotesla to femtotesla. And the gravity, again, we use atomic interferometer for gravity. So all these setups is not a far future. They are currently being done in different labs. So for example, atomic clocks we have in IISER Pune. For example, nitrogen vacancy center in Diamond, we have in IC Bangalore, we have in IT Bombay. And IISER Pune again has atomic magnetometer. So these are the experimental setup which requires very sophisticated control and very sophisticated. I mean, you have to keep the system away from the environment, any environment effect, because the moment environment is coming, they're gone. So you have to shield it from the earth. For example, if you are detecting the magnetic field, so you have to shield your devices from the earth magnetic field. So this is what, for example, we have in Nizer, Bhubaneswar. They have the lab where I have seen that they can shield the earth magnetic field, and then they can use it at for magnetic field detectors. So the work is being done at various places in India in the quantum sensing part. So this is something that we have currently mastery of. And I will tell you later that we have a kind of a national physical laboratory in Delhi, which is very big laboratory, and they sort of compare their result with the international standard for time, for mass, and for other devices. So we have this National Physical Laboratory for this standard measurements. So there are several. So apart from industry, apart from academia, there are a lot of industries which are also developing either the mostly the software part of the quantum sensing. So I have listed some of these startups here, but there are also many startups which I have missed, I think. So, but the point is that um, these startups are very much applying whatever has been developed in the theory of quantum metrology and making sort of software packages or product which people are interested in. Many companies are interested in. So since development of these devices requires very coherent research, and for that one requires very focused funding. So various countries have devoted their national quantum initiatives, including India, who has also have their national quantum mission for four pillars: quantum computing, quantum metrology, quantum material devices, and quantum communication. So there is a sort of initiative by our government as well on developing very sophisticated quantum sensing devices. And quantum sensing, alone market of quantum sensing is expected to grow as we are reaching more and more sophisticated control. We are able to understand more and more theory. So the quantum sensing market is also growing in size, and it can reach up to around 1,300 million US billion dollar by 2033. So it's a sort of an emerging market. And this can be done. What I feel that we have to work in collaboration between the academia and industry to achieve all these sophisticated devices and this precision. Okay, so now let's come to the physics part, that what actually we do here. So here is a uh, sort of a small movie which tell us that which tell us the interferometric setup. So what is happening here, that there is a wave that is incident on a beam splitter, and it break into two parts, and then it travel a long distance and reflect from mirror from both sides, and then it combines, and then it project into a screen. Now if these mirrors are located in an equal distance, then the combination of these wave will produce nothing. It will be a destructive interference on the screen. But the moment there is a difference in the path between these two long arms, you will see that the wave coming from one arm will reach earlier and the wave coming from other arm will reach later. So there is a path difference between these two. And because of that path difference, we will have a light projecting on this screen. So this is a setup, for example, has been used to measure the amplitude of the gravitational wave. So they have created literally this 4 kilometer long interferometer, and they have measured the change. They can control the change in the arm of these mirrors, which will give you this ratio, and that is proportional to the amplitude of the gravitational wave. So this setup has been used for the measurement of the gravitational wave. So not only this setup is so fundamental that you can use it to measure various things. For example, atomic interferometer. They use again a interference between the light that is going from inside and the light that is coming from outside, and they will interfere because of the gravity, and they measure it. Similarly, for the magnetic field detector, they also use the interference setup. So interference is so fundamental that you can use it to perform the precision measurement. So as I was talking about that qubit as a quantum sensor, so qubit is a two-dimensional quantum system. So it has two levels, so a ground state level and the excited state level. And that two level will span the entire Hilbert space. So, for example, here you have a 0 and 1, two labels, and they are separated by certain energy E. Now, in order to have this system as a quantum sensor, we should be able to coherently manipulate this system. Means we should be able to transfer the information from 0 to 1 and 1 to 0 and vice versa in a very coherent manner. We should not be able to lose this coherence. So what is the meaning of coherence? I will come into the next slide. But this is the idea that for a qubit to act as a quantum sensor, you have to have very well defined two energy levels so that we can coherently manipulate between these two levels. And it must be possible to initialize a quantum system in a well-known state, and also it is possible to read out its final state. So one should be able to initialize the system. So let's say I can say with 100% confidence that my system is initialized in the zero state. And when my protocol finished, I should be able to also read out the state of my system. And then this qubit has to interact with the signal that this qubit want to measure. So the interaction is quantified by the coupling and transduction. So this is a qubit. This qubit should interact with the environment, and then this the information about the environment should be encoded into the qubit, and then we should be able to read out that information. Then a qubit can work as a quantum sensor. So as we have probably seen earlier that a qubit is a two-level quantum system. It is a different from a classical bit. So classically, I have either 0 or 1. So if I toss a coin, I will get either 0 or 1. So that is a 2-bit of information. But a qubit has all possible combination, which is a possible state of a system, which also encode information. So for example, 0 is 1 bit, 1 is 1 bit, but 0 plus 1 by root 2 is also a state where we have information. So this arrangement is called the block sphere, and every point on this block sphere is a qubit, is a two-level quantum system. So for example, this pole is a 0, this pole is 1, but this point is 0 plus 1 by root 2, and then opposite point will be 0 minus 1 by root 2, and so on. So the entire block sphere is so every point in this block sphere is a qubit. You can think of like that. And how to make these qubits? So there are several proposals to make qubits. One is to use superconducting junction, the Josephson junction qubit, where we have a harmonic oscillator kind of potential. And if we remove all the higher state and keep only the lowest two state, we have a two-level quantum system, and we can make it as a qubit. So this is a very simple way, but of course, if you do go into the lab, there's a lot of complications. It's not so easy to do there. So let us consider that I have a qubit and I want to use this qubit to measure the energy difference. So, okay, so I have a Hamiltonian, two-level Hamiltonian, where I have a energy either E0 and E1. There are two energies I have, and I want to measure this omega 0, the energy difference, using qubit. So I initialize the qubit, and then I apply a Hadamard gate. So Hadamard gate, what it does, it creates a linear superposition of 0 and 1 by 1. So you might have heard in this workshop about the Hadamard gate. So it's 2 by 2 matrix which creates linear superposition. So if 0 is and 1 are given, if you act h on 0, it will create 0 plus 1 by root 2. And then I evolve the system using this Hamiltonian. So I use Schrodinger equation, which is exponential of minus I ht. So I evolve for a time t. And the state after the evolution is given by 0 plus e to the power minus I omega naught t 1 by root 2. So the information about omega naught is encoded here. But I don't know the state. The problem in the quantum mechanics is that you only outcome is either 0 or 1, not anything else. So if you measure here, you get 0 with probability 1 by root 2. You get 1 with probability 1 by root 2, 1 by 2, but nothing about omega naught. You will not get any information about omega naught. So you have to make this state again so that you get the information about omega naught. So you apply again a Hadamard gate and bring into this superposition. Now here, if you perform a measurement, you get a 0 with probability modulus of this coefficient squared, which is given by cos squared omega naught t by 2. And if you measure 1, then the probability is given by the coefficient mod squared of this coefficient. So P1 is sin squared omega naught t by 2. So if I, so this probabilities encode the information about omega naught because t is known. I know how much I have evolved the system. So t is known. I don't know. I don't know P naught with very high accuracy because I did this experiment just one time. So I toss the coin, either I get 0 or 1. So in classically also, if you had to see that what is the most likelihood outcome, you have to repeat the experiment. So in order to estimate this P naught, because the moment I estimate P naught, I can find out my omega naught by cos inverse and so on. So I have to do this experiment again and again, again and again. And if I repeat this experiment, let's say n times, then I'll get a histogram. And this histogram will peak around a value which is close to omega naught. So this is called the maximum likelihood. So the maximum likelihood occurred at a value close to the omega naught. And this full width and half maxima will give me the error in the estimation that is coming from the error in the probabilities because probabilities are never exactly estimated. And it is possible to derive that this error scales as 1 over square root of n. So this is a central limit theorem, if you all know, right? Because there are independent events. And in the case of independent event, the error will scales as 1 over square root of n. So this is just central limit theorem. But this, on the other hand, also provides a bound that the minimum error that we can get in the estimation of omega naught is cannot be lower than 1 over square root of n using this scheme, using the single qubit as a sensor, but you repeat the system many times. So that is the one limit that we can achieve. So please stop me if you have any question and doubt anywhere.
No issue, sir. Please go on.
Okay, so now we had a 1 qubit. Now if we use more than 1 qubits, what happened? So then there is a concept of what is called the quantum entanglement. So entanglement is not a property of individual system. It's a property of a global system. Okay, so if your individual system, let's say Alice and Bob, are represented by psi A and psi B, then the combined system of psi AB can be written as psi A tensor psi B, and this is a product state. An entangled state is a state where we cannot write psi AB as a product of the individual state of Alice and Bob. So we cannot write the total system in terms of the local one. Okay, so the entanglement is a property where is a global property. We cannot specify them individually. We have to specify globally everything. So that is the entanglement, I will show an example of the entangled state. But let's begin the process of quantum sensing when we have more qubits. So that is important. So suppose you have these ions. You somehow you trap these ions and you trap them in such a way that they are in the 0, 0 state. Remember the qubit, you have a 0 state and 1 state. So let's say we are initialize all the qubits in the 0 states. Then we have to apply some gate as we did in earlier case. So here, somebody has given a very nice gate which creates this kind of state, which is superposition of all the zeros plus all the one. A big superposition, not just one qubit superposition. It's a superposition of n qubits. And because of this entangling gate. Now this, if I show to my experimentalist friend, they will not be happy because going from all this 0 to this state is one of the biggest challenge that everybody is facing. To create an entangled state of large number of qubits is a very, very difficult challenge. Okay, so this, if I am showing here in a cartoon manner that we apply entangling gate and go to here, this is a separately 5-year research work that how to go from here to here. It requires a lot of techniques, a lot of you have to choose which material will give me this kind of interaction so that I create entangled state. But let's say that suppose somebody has given me, somebody was kind enough to give me this entangling gate and I have applied them and I get an entangled state. And this is the entangled state, that it cannot be written as a product of individual qubits. It has to be written in this form only. Okay. And then I evolve the system through a unitary evolution as I did in the previous case. And the evolution will give me the state and the unknown parameter omega naught that I wanted to estimate. But interestingly, my parameter omega naught here is amplified n times because of this entanglement. Now, had I have individual qubits and I'm not entangling them, I would have a 0 plus e to the power minus I omega t1 times 0 plus e to the power minus I omega t1 and so on. I will have a product of all these. But because of this entanglement, I am getting a state which encode this parameter already amplifying it n times. So I should get some advantage when I read out this state. So the reading out part again need a disentangling gate. So I will disentangle it. So I will bring all the information about omega naught into just one qubit. And then I will perform the measurements. And this measurement will give me the probabilities of either 0 or 1. And from these probabilities, so here we have some error. I think this theta will be, so this theta will be, okay, so you can see that this theta I have taken omega naught t. So this theta is omega naught t and this will be multiplied by n. So here argument will be n times theta. Sorry for this typo. And the error in this case, which is the variance in the unknown parameter, is going to scale as 1 over m times n square, where m is the number of repetition of the system. So if I repeat the system, let's say 1 time, I still get a n square advantage. So that is a huge advantage. So earlier I had a, if I go back and if I, so this is the standard deviation, not the error. So this, if you have to take a square of this, so the variance is going to be 1 over n when we have a single qubit. And if I have entanglement, then the variance is going to 1 over n square. So certainly there is a advantage of a factor of 1 over n in the case when we have an entanglement. So entanglement certainly is giving advantage in quantum metrology. Okay, so that is the whole one of that is the whole idea that we want to use, we want to create entanglement to achieve the quantum advantage in metrology, which is much better than the single qubit case. And now this 1 over n squared scaling has been demonstrated in experiment as well by none other than Professor David J. Wineland. And I hope everybody here is aware of Wineland because he has received 2012 Nobel Prize in Physics because of his contribution to the development of high precision measurement of large superposition quantum states. So earlier, the superposition was done for 1 qubit or 2 qubit, but Professor Wineland and his collaborator has created various sophisticated tools to create superposition of large many qubits, superposition of many qubits, and then perform them, use them for metrological purpose. So, for example, they have used the ion trap, or yeah, so they have used ion trap to measure uh, the magnetic field with very high precision. Specifically, they have shown this limit that so they have created entanglement and they have used that entanglement to demonstrate this limit. This is not just a theoretical limit; it has been experimentally demonstrated to the level that it has given Nobel Prize. So that is the importance of this line of research. Okay, now we can compare that if I have a entanglement of 10 to the power 6 particle, then I can achieve a precision in quantum mechanics using quantum mechanics that is 1,000 times better than the precision that I can obtain using classical mechanics. So therefore, this large entanglement of large qubit is certainly important. So that is what people call that we have to scale our quantumness to a large level to see a truly non-classical advantage. And this quantum metrology is one technological pillar where we do see that application very clearly, and we also make when people or our colleagues make those kind of experiment. So a general quantum sensing protocol consists of 3 steps. One is that you prepare your rho theta, where theta is the unknown parameter. So you prepare a state which encode the parameter, and then you perform the measurement. The measurement will give you the probabilities, and from these probabilities you construct a estimator, and one estimator is, let's say, the maximum likelihood estimator, and this estimator will give you the best estimation value of the unknown parameter theta. And if you repeat the experiment several times, you will get a histogram, and so from that histogram you can extract the error. But where is the quantumness? The quantumness here is in this state. In this step, if the state is quantum, then of course the histogram is going to shrink further. And if the state is not classical, then of course this histogram is going to be remain wider. So that the widerness or the shrinkness of the histogram is going to determine how precisely you are able to measure your unknown parameter using the tools of quantum mechanics. And we have seen that the quantum mechanics does provide a fundamental limit, lower bound, that you can reach. If you can reach 1 over n square limit, then of course that is the best possible precision that we can achieve. And this method that I have explained is used in various applications. For example, atomic clocks, magnetometry, and gravitational wave detector. This is what they use. They prepare, they measure, they estimate, and they extract the error. This is the step involved in any quantum sensing protocol. So a general theory of quantum metrology is very big. It involves statistics. I'm not going to go into detail there, but the idea is that Kramer-Rao inequality determines that what could be the minimum error if one perform the measurement of an unknown parameter, which is basically the variance, right? I mean, the estimated value minus the actual value squared and average over all these measurement outcomes, which give you the error. And this Cramer inequality says that this quantity is greater than the inverse of the quantum Fisher information. The quantum Fisher information is a geometrical tool which tells me that how far two quantum states are. So the parameter estimation is related to the distinguishability of two nearby quantum states. So if phi is a quantum state, depends upon mu, and phi mu plus delta mu is another quantum state, then whether we can distinguish these two quantum states or not is determined by the quantum Fisher information. Okay. So this is the first part. The second part is that the quantum Fisher information requires optimization over all the measurement, which is again very difficult task. What is possible in the lab is certain measurement are possible in the lab. So if we have a given measurement, then what we get, the information about the unknown parameter we get is known as the classical Fisher information, and the corresponding Cramer-Rao inequality is known as the classical Cramer-Rao inequality. Now, the problem here is that this bound, achieving this bound, so so this is a less or equal, greater or equal to, means there is a state, there is a measurement, there is a estimator for which we can achieve this bound. But what is that measurement? What is that estimator? We don't know a priori. We have to really indulge in more detail to find out all these details. We know that if we have entanglement, we can achieve to certain state. That is something we know. Okay, but for that we have to create entanglement. So so all this optimization, whenever there is optimization involved, you can understand that these things are not very straightforward, and you have to have to do a lot of physics and mathematics there. Anyway, so the Fisher information, when the Fisher information is case n square, where n is the number of qubits, then it is called the Heisenberg limit, and then the error will be 1 over n square. This is what we have seen. So what we understand from this first line, that larger the Fisher information, lower is the error. So we have to have a system, uh, the estimator, and the state which give us the highest Fisher information, so that we can measure the parameter with a very high accuracy. The standard quantum limit is one where the Fisher information is scaled linearly with n, and then the error will be 1 over n. This is we have seen for a single qubit case. Right? So this is a general theory of parameter estimation. And these are two very important limits. So we always try to find out a system measurement estimator which give us the highest quantum Fisher information in terms of the number of qubits. Now, what I have said earlier, that noise is always a problem whenever we perform any measurement with quantum system. Whenever we have a noise, it will destroy quantumness and we will lose all the advantage. So, for example, in this Ramsey kind of measurement with a single qubit case or with the entangled case, whenever there is a free evolution in experiment, it is not exactly the free evolution. It is involved with a lot of error. So free evolution is something that where the system will interact with the unknown parameter and try to encode it. That free evolution is full of errors. And that is modeled by this dissipation or dephasing term here. And we can see from here that because of this term gamma, the quality of the estimation decays with gamma. Right? So there's a gamma factor here. So because we have a noise, so the noise will try to destroy our advantage, the quantum advantage, which is also clear from here. So as we evolve the system in time, the entanglement will quickly disappear and it will reach to a minimum value of the error that give us. So it quickly deteriorate the entanglement. And it is so bad that it will be actually same as the one obtained by the uncorrelated states, the minimum value. will be same as the one that we can obtain by the uncorrelated state. So, of course, for example, these Z kind of state, they are very fragile. I mean, exponentially fragile with the noise. So you give the noise and exponentially time, they will just decay their coherence. They are not very useful in this case because to work with the Z or the max. So this Z means that this state, so this state is a called the G-edged state because this is developed by three scientists called Greenberger, Horney, and Zeilinger. They have sort of developed this state. That is why they call it G-edged kind of entanglement. So that's why I have been saying G-edged state and G-edged state. Okay, so noise is certainly bad for all kind of these measurements. So the other platform for quantum parameter estimation is many-body system, uh, where Professor Sumansi is an expert on that. So, so many-body system consists of a lot of particles and they interact with each other in a very unusual way. Okay, so for example, if we have a quantum XY spin chain, so these individual particles are spins and they interact with this kind of interaction. And suppose the system is disturbed by a small magnetic field. So the total Hamiltonian will be written by this H. And the goal is to find out H naught. Can we do that using this system? That is the question. So there's something, a nice property that the system hold, which is called the phase transition. So when the system is in the ground state, and if we change H naught, then we go from one phase to another phase. When H naught is less than 1, or H naught is less than J, we have a ordered phase. And when H naught is greater than J, we have a disordered phase. And what happened around this phase, this point, that a very small change in H naught give us a large change in the microscopic state. So our system will change drastically with a very small change in the parameter around this point. So this point can be used to, you can use as a detecting the small signal. So the many-body quantum sensors, when I say what I mean by that, the system which exhibit this kind of phase transition property. So this system exhibit what is called the second order phase transition when gamma is equal to 1 and H naught is equal to 1. So this so J is 1 here in this case. And in that case, this system exhibit a second order phase transition, and second order phase transition can be used as a quantum sensing point. So how we do that? So let's say that we have two quantum states which are nearby. So we are differed by just a small dh. So we can expand this other state and we can take their overlap. So this overlap is called the fidelity. Fidelity means how close two things are. I mean, so you study the inner product in your class, that how similar two vectors are, you take their inner product. If the inner product is 0, then you say that these vectors are orthogonal. If the inner product is 1, then they say that the two vectors are parallel to each other, so they are same. So that is what we calculate in the fidelity. So when the states are same, then the fidelity is 1, and then there is a first order change in the fidelity, which is 0.
Please mute your mic.
And the second order in DH is called the fidelity susceptibility. So fidelity susceptibility measures the stiffness of this function as a change in the parameter h. And it is known that at the critical point, this fidelity susceptibility scales as n squared over d nu, where d is the spatial dimension and nu is the critical exponent. So for this Hamiltonian, d is 1 and nu is 1. So chi f at SC goes as n squared. And away from the criticality, this scales as linearly with the system size. And there are well-known understanding in the community that the Fisher information and the fidelity susceptibility are related to each other. So what we can see from this relation that at the critical point, the Fisher information scales quadratically with the system size, and away from the critical point, it scales linearly. So now you can relate that this system give us Heisenberg scaling at the critical point, and a standard limit away from the critical point as far as quantum sensing is concerned. And this is what back in 2008 people have realized that critical quantum system can be used as a resource for quantum estimation. And away from the critical point, one has to have a linear scaling with the system size, and away around the critical region we have a quadratic scaling. So critical quantum systems are a resource for quantum metrology. What we did in our paper 2-3 years back, that suppose we do not measure every particle, we just measure a block of particles. Okay, and on top of that we apply a time dependent term in the Hamiltonian. Rather than just ground state, we look at the non-equilibrium dynamics. So this is our system, this is the parameter that we want to estimate, and we apply a time dependent signal with known frequency omega and known amplitude h1. So we know this, the thing that we are applying to the system, we are aware of these parameters. So then the question is that if we just measure L qubits out of n qubit and we use this system as a sum as a system to detect an unknown signal h naught, then can we achieve a Heisenberg kind of scaling which goes as L square? So remember, the Heisenberg scaling goes with n square, not with L. That is not known so far. What happens if you have only part of the system? We are trying to know whether we are able to achieve L square scaling even with we measure part of the system, not the entire system. So what we have found that if we drive the system with a right frequency, so here we have taken omega naught 2 and omega naught 1, and we are still at the critical point, we found that indeed we are able to achieve the L square scaling even by the measurement of the part of the system and not the entire system. That is sort of a new result at that time in 2021, and we published this paper in Physical Review Letters. So the summary of this paper is that people often try to measure everything and then achieve the Heisenberg scaling. We achieve the Heisenberg scaling by only measuring the part of the system, but with the help of a time-dependent signal where we can control the frequency. And this advantage is related to what is called the Floquet resonance. So there are certain frequencies where there's something called the effective Hamiltonian. So this is a time evolution operator. And this time evolution operator can be decomposed into what is called the HF, the Floquet Hamiltonian. And the Floquet Hamiltonian, if you diagonalize this Hamiltonian, you get the energy eigenvalues. And you plot the energy eigenvalues as a function of H naught, you will see that there are points where the Fisher information is there are points where the Floquet gap vanishes. And these are the point where we have a maximum Fisher information or maximum scaling of the Fisher information. So this is the physics behind this L square scaling. So we also perform the same idea for AC field sensing. So far we were developing the DC field. We also use this for the AC field sensing, where HT is a time varying field, not the single field. And we again find that the Fisher information is peaked in a certain areas, and this peak correspond to the area where the Floquet gap is minimum. So this delta F is the Floquet gap, which is the difference between two uh, energy levels is minimum, and where this is minimum, we have a maximum Fisher information. And when we perform the scaling with respect to subsystem size, we saw that around the critical point, we have a scaling that is close to 2, not exactly 2, but certainly away from the critical point, we do not have the L square kind of scaling. So it means that this technique that we have proposed can also be used for the AC field sensing as well. And then we have developed a lot of protocol using many body system, and together with Abol, Matthew, Chiranji, Victor, Rosin, and Soubik, we have written a physics report, which is a review article on quantum metrology and sensing with many body systems. So if anybody is interested, you can read this paper, and if you have any sort of a doubt or any comment on this, please feel free to share with me. There's also a recently very nice review on critical quantum sensing, which is a very student level topic for which is a tutorial topic that using the so this is on parameter estimation near quantum phase transition. So these things are something that are now for last 2-3 years are very much in the community, that critical quantum sensor, many body system which undergoes a quantum phase transition can be used as a magnetic field sensor. So far I have discussed the many body system. If I have a time, I can discuss a little bit about the our other work, which is about beating the standard quantum limit using single photon array coherent state. So we here consider this interferometric setup where we have input lights at the mode A and at the mode B, and then there's a beam splitter. Okay, so the light A is coming from here, it is split some part to in this arm and some part is transmitted, and similarly for light in the B mode. But here, of course, there's an unknown phase that is coming from somewhere in the form of magnetic field or electric field, and it disturbs the light that is going from here. Okay, but one can write down the, so this one can measure the photon that is coming at the output. And from the photon, one can measure the number of photon at the port E and the number of photon at the port F, and their difference will give me interference pattern. Okay, so what we can do, that if we have a vacuum and coherent state in the mode A and B, then we have a standard quantum limit that is sort of known to people. Now we all know what is the coherent state mean, right? I mean, it's a superposition of the harmonic oscillator state with different weight factor. So coherent, and so what we tried here, we tried that if at the port A we input coherent state and at the point B we input the single photon array coherent state. Now the interesting point is that the coherent state is a classical state. It is minimum uncertainty state, right? But the moment you add one photon here, the state becomes non-classical. That is what shown by Professor Agrawal and collaborator back in 1991, that this state, SPAC state, is a non-classical state. So we use this non-classicality to detect the phase phi. So there is a gray region. The gray region tells us that if this line crosses this white region and reaches to the gray region, then we have a quantum advantage. It means that the uncertainty due to the classical light is beaten because of the SPAC. That is the meaning. And we indeed see that SPAC beats this region. So it reaches to the region. And if we add two sort of, yeah, so I don't have those plot, but the idea is that for a certain range of n, we indeed see that we are beating the standard quantum limit, which is given by 1 over n. So we're beating that 1 over limit by adding the single photon coherent state. So, okay, so people are also using machine learning in quantum metrology. So this setup is same, that you have a state preparation, then encoding, then detection. Then you feed this measurement outcome into the neural network, train it, get a probability distribution. From this probability distribution, estimate the parameter, estimate the uncertainty. And if this uncertainty is sort of not up to the mark, you repeat this again and get to the best uncertainty. So people have using machine learning. People have been using what is called the quantum computing techniques to obtain the better and better precision. So these are the people from MIT who have proposed a new limit that if they use quantum computing methods, then they can even go better than the Heisenberg limit. That is something very new development. I thought it is better to tell everybody. There's a nice essay by Peter Joller and UN about the current development of quantum metrology, quantum sensing, and their application for discovering fundamental physics, like the dark matter. So one can use these tools for detecting dark matter. The details is something that one has to look at it, but these are some new development that I thought to share of. So in summary, what I want to tell that quantum sensing is better than the classical, but it is weird. It involves entanglement and other sort of concept. And the revolution due to the quantum sensing is here. We do have techniques, machines, and devices which are based on quantum rules, and they give precision. And as earlier we had different kind of tools for measurement that were not sophisticated, but as we grow, our life were sort of improved by the new measurement tools. In a similar fashion, quantum technology will sort of continue to shape our lives. Now, I just want to finish by that there are a lot of open problems in quantum metrology, which include multi-parameter estimation. That if you have a more than one parameter, then how to perform the measurement and what is the ultimate limit of precision and so on. Also, the use of neural network, quantum control, error mitigation, and error correction in quantum metrology, and also hybrid platforms. So, suppose we have a spin, we have light, and we have other system. How do we combine them and sort of get the best out of this? These are the things that people are still working on it. So most of the work that I showed here has been done when I was a postdoc at UST China with Abol and Victor and Rosin. This work is done at the time. I continued this work when I was at Southern California with Daniel and their team. I have long-term collaboration with Devraj and his student Ayan on quantum metrology. And recently I have been developing new collaboration with Pankaj and Konstantin on the quantum optics and quantum metrology. So at DU, I have a student, a master student who sort of learn new things and try to sort of work on the new directions. So Lakshya, now he's in IMSC Chennai, Chirag is in Sweden, and Aditya is in HRI, who is working on different projects. Okay, so with this, I think I would like to thank you for everyone for their kind attention, and I'm open for the questions.
Very much, Dr. Utkarsh. I'm just first curious about your last slide, thank you slide. What is the message you are giving on that slide?
Oh, I
Just a
got it
funny
from
one.
I got it from that movie, right?
Yes.
And everybody was paying attention. So thank you for your attention. I hope.
Okay. Thank you very much for a wonderful presentation on quantum metrology. With so much patience, you have, I think, the person who is like seeing this presentation from 1 hour can learn the basics of quantum metrology in a very, I cannot easy way, but in a very good way. So thank you so much for giving us the about fundamentals of quantum sensing, why it is important, and what is happening around us, right? So thank you very much. Now we are opening for questions. Please participant. You can have a question on chat box on WhatsApp, or you can just raise your mic. Then I will ask my question actually. Any question? Yes. Your voice is not coming. Your voice is not coming, Peter. No, it's not clearly coming. I hope it is coming to everyone. Voice is coming to everyone.
Yes, ma'am.
Okay, Devanshu, you can ask. You're on mute, huh? You can ask. Yes.
As we previously talked about atomic clock, which was several times in 150. So, is there any particular temperature that we need to maintain, or at the room temperatures we can complex?
Yeah, that's a very good question. I think you do not need any temperature there, except that you have in that region where you are trapping your atoms. Because you are trapping your atoms, the temperature is of course lower because atoms are not moving, right? Because you are creating this vapor of atom from somewhere, so they are very heated out and they are traveling here and there. So you have to cool them down. And to cool them down, you have to put laser from all the six direction, and there the temperature is of course much lower than room temperature.
Small number of scenarios, technical methods for which you can use noise, which are being created with consumer level.
How to reduce the noise?
Yes, sir. So we will thermal fluctuations or magnetic interference created by the light.
Yeah, so right. So for other magnetic thing, you have to shield it. You have to use the magnetic shielding to shield the other magnetic effect. For thermal fluctuation, of course, you have to reduce the temperature of that region, the box that where you have a trap. Yeah, so for sure, the noise is the main hindrance for achieving the best out of quantum.
Yes, sir.
Thank you. Nice questions.
And anywhere else, please, Reese, you can unmute your mic and you can put in a chat box. Any query you have. It is not something very technical. Any idea you have in your mind, you can just put it here. We are ready to listen. I have a one question, Dr. Mishra,
Yes.
that you told us, right? You told about Kramer-Roy inequality, right? Kramer-Roy
Yes.
inequality. I want to know the full name of that scientist Rao you have taken, because we should know our Indian scientists. Whenever I see some
Okay,
person,
so
yes.
I apologize because I think recently the Professor Rao passed away. I mean, he was in India and then he retired and then he went to US. He joined the position there. But yeah, I have to look at the full name because I just use always Kramer Rao.
Camera, yeah. Because there are, we normally, as in scientific community, we don't give much credit to the, no, not credit, we don't know mostly, and our student even don't know. And in academia, there is a very perception, okay, that in Indian academia is not as good as outside, right?
No. So Professor Rao is one of the leading statistics.
Yes. That's I know.
Yeah.
That's I know. That's why I want to know my
Thank you.
participant. Yes, please go to Google and check it, and you must remember his name because he's a pioneer in quantum sensing.
Yes.
Okay.
Yes.
So, and we must pay homage to him, right?
True. Very true. Yes.
That's why.
I do.
Because
I admire him a lot. Yeah.
yes. Because whenever I have a my physics class or any class where we have an Indian scientist, like we have a Bose-Einstein theory and any, I just first I tell student briefly about their research. At least 1 minute they know what is a Satyendra Bose, and if any Indian scientist is there.
Right. That's true. Very true. I think
Yes.
I will do this as well because he particularly is very much just I am fan of his work actually.
Yes. Okay, and I have just one question about see, I have like a lot of question because I as remember uh, quantum tweezers, right? I think recent Nobel Prize is awarded to a person about quantum tweezers, right? If you recall.
Oh, this year was
No,
regarding
not
my.
this year. I think 2 year or 1 year back about quantum tweezers, if I remember.
Okay.
Okay, so I thought maybe maybe in some other time we can discuss about this. So because our next speaker is on the line because we have a presentation from 3:30. So Mr. Divyanshu, please present a certificate of appreciation to sir because sir have given us like a wonderful talk with wonderful topic, I will say. So Dr. Mishra, we are really grateful and we heartily recognize as an invaluable contribution as a speaker for this course,
Thank you
which
very
is
much.
jointly organized by Department of Physics and Institute Innovation Council Incubation of HB2 Kanpur. We deeply appreciate your dedication in sharing your knowledge, expertise, and insight on this topic, quantum metrology and its application. And your time, effort, and your discourse greatly enrich the learning experience of all the participants. Thank you so very much, sir. And I hope we can also offline call you on any event in HB2 Kanpur as a person. in future, near
much.
future.
Thank you so much. I would be great. I'd be happy to interact with you guys in person for sure. Thank you so much.
Thank you so much, sir. Thank you. The participant, I think our next speaker already have joined the session. Dr. Senthil Kumar, can you hear us, sir?
Very good afternoon. I am audible.
Good. Yes, yes, you're audible, sir. Little bit voice is slow, I think.
Yes, it is right now. It is okay, ma'am.
I think it's fine, sir. So our next speaker is Dr. Senthil Kumar. So first, I want to briefly introduce my participant. That Dr. Senthil Kumar is a senior assistant professor and researcher in KIT, Coimbatore, Tamil Nadu. He's an academician and research professional with 15-year experience of progressive experience in artificial intelligence, machine learning, generative AI, quantum computing, data analysis, and emerging technology. He has a national level resource person for most of the faculty develop program, workshop, seminar, and technical boot camp. He's a certified associate in Nevada. He's a certified Intel instructor, and he is a certified IBM Power Skill instructor. So, sir, have a very long profile in quantum computing, and a lot of, I think, a lot of because of his interest in quantum computing, I invited sir. So please, sir, I welcome you with my heart to this event. Sir, over to you, sir.
Thanks for the introduction. It is my pleasure to share my thoughts and my interest in research areas in the quantum computing.
So your voice is not very clear, I think, or me to or
one
everyone.
second.
I think some background noise is coming.
Is correct?
Or maybe some speaker is on. Devanshu, can you check, please? Acha, okay.
I'm audible right now.
Sir, you are audible, sir. You can share your PPT.
Okay. I'd like to thank Divya ma'am for this opportunity. So I share the screen.
Yes.
Hope my screen is visible to all.
Yeah, it's coming, sir. It's coming.
So myself, Dr. Jason Kumar. So directly we will move to the topics. Then we'll have some. I like to show some hands-on which I created myself for understanding purpose, which is working on an UI UX based application. So as I like to share that from the basics of my quantum, then I try to share some topics like data structures, IoTs, and AI related, then cloud. Last sessions I have seen some sensing techniques which is used in quantum. So with that we had to integrate with the applications like we had to go for with some integrated method for the future, right? So this is a basic for all the kind of an structure like an AI, IoT, cloud, as well as sustainability, which is used for the natural world, right? So basics, as you know, that quantum it is an computations that which is used by the computer science and then like an quantum mechanisms. So it is an emergent field for the computer science and then engineering that harness that unique quality of an quantum mechanisms to solve the problems beyond the ability of even the most of the powerful computers, right? Here we are going for an actually in my field in my sections, like what I feel that when we have some storing of the data in the form of an fire, okay? We are storing in the form of the data in the form of an fire. Now I feel that we are moving to the form of an sphere state. Okay? So here we are discussing more about the sphere. We have block sphere, right? So how we are storing and how we are accessing the data with the help of an like an qubits, right? In classical computers, we have in the form of an zeros and ones, and in quantum computers, we have qubits like an so position of zeros and ones at the same time.
So this is a little bit basic of quantum. So we all know, right? I like to share some working principles what is going on the quantum. So as you know that we have the hardware like and how the data is like qubits, like an classical bits are sent to this process of an cloud areas. Then from the classical, it is converted like an yeah. So you can see that that is an specific job which we are applying to that with the help of an cloud. From that, we are moving in the form of an we are transferring the qubits in the form of classical to that server area. It is moved to that in the quantums and it processed here. Okay. So all the process is taken and we can see that the measure of the pulse intact and we can with the help of an qubits via read out and send. Okay. So here we have that like an semiconductor devices, which is and we are calling as a quantum processing unit. All the process is done here. Then after getting the output, it will be transferred back to the positions. Uh, here, one thing is we have to know that with the help of an atoms, it will be stored with in the process, the measure of a method by a circulator. Isolator prevents and noises from the getting to the bits. So it will be transferred back to that server, and you'll be getting this with the help of the measurement. We will be getting the output. Right? So this is a working principle of an quantum computing, which is taken in the from the IBM. IBM, which is working in the process. It is started from the classical qubits and it is processed here with the help of the measurement. We are getting the output. Here we have some like and we have that semiconductors which is used for the measurement and like an atoms with spins and a lot of things has happened that like an spinning of the atoms and the entanglement and the superpositions and those like an inference we have like that. Right? So this is an process which is taken in the quantum. Then I like to share some roadmap of an quantum. That is, we see the map of the quantum. Then we'll have the picture like this, right? So what is going on this quantum computing is first we have started from the quantums like and superpositions. Then we have some entanglement based upon the probabilities. We'll be getting the values. Here the measurements done with the highest measurements we'll be getting the values. Suppose if in this example I have shown of an 1 0 it is in higher position, so that entanglement is which is present in this area, right? We have that superposition entanglement interference which is happen upon 3 qubits. Then we have the inference that is a wave forward. There is a wave function which is happen in the quantums to calculate that wave function, right? In the form of an cos and sine, right? Then I have to show some concept like an the model of the quantum computing. So as we know that we have that techniques to calculate it often errors and we have some quantum analysis. Then we have the topological quantum computing which is happen in the quantum. I like to show that of a quantum algorithm. So here, what is the calculations is done with the help of a Shor algorithm that is used to calculate the factorization. So for the calculating the factorizations, it will be taken a few seconds to calculate the factorization. Suppose if you are going for an classical qubits, it is you have to take right, you have to multiply and you have to go for with the help of the quantum algorithm. But in this factorizations, it will be splitted easily with the help of an Shor algorithm. So I will show some Shor algorithm examples. Then we'll have some discussion in that. Then we have that like an n NNP complex, right? So the how much harder in the solve the problems with the help of this NMP, and we have the quantum complexity theory. So this is an Shor algorithm how it is calculated. So these are the things which happen in this real time. When you're going for quantum simulations, that is an we will keep focusing on the finding the drugs like an drug discoveries and improving the batteries, and we have that back like want to simulate for the large quantum systems on the quantum computers, and rapidly we have the prototypes. Many different materials will be done with the help of it. So main idea of the quantum computing is to find the complex. Okay? Suppose if we want to find an infinity state, we have to use the quantum computing to identify infinity. So in the real time, we have that nowadays we are focusing on the machine learning and AI concepts. So it will be in next futures we do for the climate changes and for weather weather forecast, and we are going for mainly we are focusing the quantum in the form of cyber security for hacking your username and passwords. Then with the help of quantum, it will be easier in this state, right? So these are the potential applications of quantum computing. Then we have some physical relations like an superconducting quantums. As you know more about this, right? We have some devices to calculate the flexible qubits, and with the help of magnetic flux or then quantum interface. And then we have the frequency changes, which is used for the oscillations. The copper pair will be used. So we can focus on the trapped ion, which we are sending the laser lights. Then with the help of an energy levels of the atoms, it will be vary. Based upon that also, we can calculate about the quantums. So these are the techniques which is used for the semiconductor devices. And we have the other approaches like an electrons on helium qubits, cavity of an quantum electronics, and then we can have the nuclear magnetic resonance, and we have the magnetic molecules. So these are some map of the quantums which can be used in that quantum computing. Right? What is this purpose of this map is? You should have to know about the classical gates, and you should know about the quantum gates, which is calculating your we are calculating the output of the measurement, right? Measurement is based upon this, right? So for this map of the quantum computing, you can see that how it is being used in this. Here we have the techniques. So maybe you may have seen before this. Again, you can see that quantum state. Okay. As you have to give them, you can see that it's here, and we have some storages formatter, right? The changes on the data set. So here, what I am showing here is that is the state of the quantums, which is can be and vary in the state. Okay. So what is the purpose of this? We can store the data of gates and mode. Okay. When we are applying the gate directly, then the value is calculated, measured in the calculated in this part. So here we have the fundamental practice like an atoms, electrons, and protons, which is calculated in this part. Okay. And we have some quantum analysis will be done, and everything is error corrections. So here, what is an error correction? We have fault-oriented quantum computing. There are many noises will be generated, as we have seen often. We have covered with the help of some devices, right? So that is the physical qubits. The how many needs often depends on the quality of qubits. We have to measure that. Then finally, we have the perfect quantum qubits will be generated with the help of a probability statement. So this is we have estimated of 100 to 1024 qubits will be generated. Okay, for the one shot of an quantum, it will generate 1024 qubits. That from that we have to identify the from the probabilities of we have to identify which is an highest value. And then we are measuring the values. Right? This is the map of quantum computing. Then we are going to see about that. What are the companies is available of doing this quantum? So here we have the supercomputing quantums, and we have the IBM, Google, D-Wave, Intel, and we have that NVIDIA also is moving right now, right? So they are generating more number of qubits. Recently, we have some helium, and below we are generating more number of qubits right now. In India, we have Kaveri quantum, which they are generating 64 qubits, right? There are a lot of companies are working on the quantum computers. Then you can see the quantum dots and quantum computing. So that silicon spins and quantum computers, which is in electrons. It is done with the help
Dr.
of
Kumar, just a minute. Hello.
Ma'am, I'm audible.
Yes, you are audible. Sir, can you, I think little bit fast, we have to catch with you. Little bit slow, I think. If you can speak, then it is better,
okay.
sir.
Yes, ma'am. Yes, ma'am. Actually, there are a lot of concepts is there to explain, so I am
Yes. A little bit, sir. Okay, thank you.
Yes, thank you. Right. Here we have the companies. What you are seeing here is in this form of Jan 2022. we'll start that. Uh, like I like to share often entanglements. So here that objects, I mean the quantums, that if you measure that that is an entanglement. So if you measure that one qubits, it automatically you can measure the zeros and ones at a time. So this one we are calling as the entanglement. And we have that block. Okay, I like to share this one. Okay. Superposition. Qubits represent multiple states and ones, allowing the quantum computers to compute the many solutions in parallel. That is a superposition. And the entanglement, the qubits can be linked, so they are share the information simultaneously. This enables a new algorithm and vast increase of quantum computation powers in the quantum entanglement and inference, then measurements and decoherence. So these are the points which is shown in this part. Okay. We have that of data. Here we have the inference. There is a wave which we can be calculated here, and we have decoherence in this. We can calculate in this part. Decoherence is a process in which a system of a quantum state collapses into a non-quantum states. It is triggered by the measuring of quantum systems or by other environmental factors. It is done in the decoherence. Why we have go for measurements? When you're going for one shot, there is an 124 times it will be running. In that between, we have to measure our what is the value. There is a reading a qubits collapse in its states. It into and define definite classical values, providing a probability solution based on the quantum algorithm. So this is one we are calling as measurement. So here, from this quantum principle, we have seen about entanglement. When we have that value, we want to find the value of when we are measuring the values, automatically we can identify what state we have. Okay, zeros are and ones. From that we can identify that. So this is we can say as entanglement. Then we have block sphere. So in block sphere, you can see that value of one block sphere is the z-axis, and we have it x-axis. Okay. So you can see the values of an x-axis, y-axis, and z-axis. And the y-axis we have that I gate, and you can see that in the opposite we have the minus gate. In x gate we have that we are calling as plus and minus. Okay. We have the value of an plus and minus in the x gate, and y gate we have the 0 and 1. Okay. So this is a like an in the sphere, we are assuming the values of the like this, right? In the z gate, okay, we have z axis, we have zeros and ones, and we have the y gate, like in y axis, we have that I axis, I and minus I, and in the x we have the plus and minus. Okay? So what is the representation of these values? If you are going for an z gate, like an zero gate, it is represented in form of an ones and zeros. If it are represented as one qubits, like an one gate, here this represents often zeros, zero and ones, right? If you are going for this part and this part, like we are going for a Hubert gate, right? So for the Hubert gate, H gate, we have representing from 1 by root 2, that is in your kind of superposition. Okay? So this part we are representing in form of superposition, and suppose if you going for the I gate, okay? I gate it is represented like 1 by root 2, comma I by root 2, and in the minus it is represented as 1 by root 2 minus I by. Okay, this is the representation of the sphere. Okay. Now you can see that suppose if the state is presented here, okay? If it is presented in this part, we have that like an psi and theta will be calculated. So with the help of an alpha and beta, which is already we can calculate it. Okay? So that superposition, when you are going for representing of these positions, we had to use that alpha and beta to calculate the values. If the alpha square is the probability state, then the state is in the form of an zero case. Okay. So here before this, you have to you know that you can see that if it is an 8, okay, we will be calling as brackets. Okay, bracket will be represented in the form of 0k, so like this, right? So which is represented in rows and columns. We have representing, always we are representing in the format of an, rows and columns of an qubits, right? Alpha qubit, alpha 0 qubits and plus beta gates. Okay, so I am representing as an A and B. It is represented in the form of an 0 gates, and it is represented in form of 1 0. So always it will be as an 0 when we calculate both the values. So this is a superposition part. So for an example, if you are a value of like this, right? The matrix representation of the qubits, we have the 0 qubits, that is an we are calling as an 1 and 0s. Then if you are going for 1 qubits, we have the 0s and 1s in this column. When we have the bracket, so it is represented as 1. So it will be calculated with the help of this like an row and column filters. So when we have that 1 and 1 bracket, we have that values as 1. Okay? When we have both zeros and ones at a time, so the value will be in form of an 0. Right? So this is the representation of a matrix, and here we can say that psi which is used for like calculating this value. When for an example we have a 0 qubits, ones and zeros. Okay? So when psi of k, when psi k, it is represented in form of an alpha A and B. Okay? So this is a matrix representation of the superposition. From here to here. We'll take some example of this state. Suppose if alpha is an root 3 by 2, when we are measuring the values, when we measuring a one beta, that we will get an 1 by 2 2. So what is the probability of measuring the values? Here is, we can say the measuring of 0 is 3 by 4 and measuring of 1 is 1 by 4. So the calculations is done here. Here, what is how it is done? We are representing as psi 1 equal to root 3 by 2, and let us consider that values like an alpha square and beta square equal to 1. Now psi 1 is equal to root 3 by 2 and 1 by 2, and beta's value is root 3 by 2 and root 2 by 2. When we are calculating this value, suppose if you are representing a 1, this here it is not equal to 1 2 here, so alpha is stronger. Okay. For calculation, okay, for root 3 by 2 whole square plus 1 by root 2, so we will get a value as 1. If it is not equal to 1, then this one will not be calculated. Okay. So the psi 1 is the validate state, and psi 2 gate is not a validate state. So this is how we are calculating that superposition state. Okay. Next, we have so how the gates are working on? We are giving the input to that gates, I mean pattern gates. That is will be we are getting the form of a cycle. Okay. So this is the logical gates. Like we have that unary gate. Okay, we have that unary gate. When we are apply the okay. So how it started? So started from the classical qubits. We are making into an qubit stakes. Uh, From the qubit stakes, we are moving to that quantum gates. Okay. So finally, we'll be getting the values in the form of one classical qubit. Okay. So that is a representation of one. We can also give an input in the form of an classical qubits. Then we'll be with the help of an quantum qubits, we'll be getting up from classical or an qubits. Okay. So both the states will be getting the values with the help of an quantum gates. Right? So these are some quantum gates. As you know about Hermit gate and T gates, CNOT gate, Tofel CNOT gates, poly is a gate, is that rotations and NOT gates. And most one we have that poly of X gates, like an measurement. Okay, error corrections mostly we will be using of an X gate. And Y gate, so it is represent the matrix or values from the constant zeros, 1 and 1 0. Right? We have the polygate of y with the 0 minus I, 1 and 0. It is a representation of an y cube. Then Z gates, S gate, T gates, Hermite gate. So again, this is a value representation of an Hermite gate in the unitary matrix. So Hermite gate is the transfer of the basis state into an even position of the two basis bias state. So T gate, which is used for the relative phase of pi by 4 between contributing the bias states, sometimes called as pi by 4. Okay, because the diagonal elements can be in the form of an e power I pi by 8 and e minus I pi by 8 and I pi by 8. Okay? So T gate is be used in this, okay, in this structure in this form of a matrix gate. Then we have C naught gate. You can see the swap gate. Okay, this part we will be using for a swap gate. It is represented for the in the classical of an XOR gate. Right? The input is connected to the solid dots and passed through the to make the operative of reversible gate. So it is one of the reversible gate. Then we'll go for the CC naught, which is for the control naught. A 3 qubit states that switches the 3 bits for the states, where the first 2 bits for the one that is switches from the state. Okay, likewise it will be changed. Likewise, it is in the form of a reversible gate. Okay? And we have the AZ gate, there is a minus gate, and like this. So these are the gate representation of a quantum. Uh, I like to show some like a phase how it is represented in the form of an mathematical related. Here one some like an real view of an quantum phase state, right? Okay. So we have some phase of state. Suppose that position okay, x gate, which is represented x, and it will be an wait one second.
I think participant, please mute your mic.
So how it is calculated if you are going for an Z gate, X gate? You can see how it is calculated here. Okay, suppose the position is 1 by root 2 0 qubits and 1 by root 2 of 1 qubits, that is an superposition state. So when you are applying that Z gate, so it will be in the form of minus. Okay. So when this is the output, okay, when you suppose it is in the form of an plus gate, when we apply z gate, automatically it will move to that in this area. So in this gate of minus, okay. So how it is done? Suppose if you have the z gate, when you apply for the plus gate, it will be you will get the value of an minus 2. Okay. So it is in the form of an error correction state, like an which we have like this. So how it is moving? So here I'm going to change the position like an that is minus 1 is represented as plus e power I pi. Then that e power I pi will be change the values of an state from one state to another state when you applying the optimal state. Suppose the position of an is that the plus state, and we have position of an I gate. So I is equal to an e power I pi, and there is an upright in this part. Okay. So we have that global phase and relative phase in that sphere state. So e power si, which is applied here in global state, it will be good for the all the states, right? When we go for a relative phase, we have the values in the form of an theta state. We will be discard the global phase in this example. So the calculation is done. So this is a calculation of an phase gate, like, and when you go for applying of an exit gate, that value will be changed with the help of an alpha and betas and with the help of AI side. So now, so up to this we have seen about the basics of the quantum, like and how it is started. I'd like to compare with an high processing computing and then supercomputing. So as you know that this is quantum computing is high and efficient to as you know that we have that super processing for the high computation powers. In within a few years, a lot of changes is going on the quantum. So like we are modifying that high computations with the help of quantum. So here is some comparisons about the quantum computing, high processing, and supercomputing. So from starting of an base unit, like and when we go for the base unit, it is the classical qubits like in we have our kind supercomputers like in the form of zeros and ones. In high processing unit we have like zeros and ones. Then in quantum, as we know that there is an qubit state of zero gates and one gates. So what is the core principle of the supercomputers? It is an deterministic digital logical will be used here. And in supercomputers, we have super performance computers. We have parallelisms within thousands of classical processes will be used in the HPC. Finally, we can see that quantum computers often we'll be using the quantum mechanism as a superposition and entanglement. How it is doing? We are using in the form of parallelisms that is in sequentials or in limited parallel. In HPC, we have massively parallel via CPU and GPU clusters. In quantum computing, we have an quantum parallelisms. All the superposition states operates on once. So, like when we go for a one shot, we will be running of 1,200 shots. It will be running in the quantum state. In scaling part, the linear with the number of bits and the linear with the number of cores and nodes, and we have the exponential. We will be having some exponential states with the number of qubit states will be calculated in quantum state. Then again we have some comparisons like and the speed of the drives will be an clock rate, rasterizations, parallel processing, distributed memories, and quantum operations is done. We will be using a quantum operations with the help of quantum gates and entanglement with the calculations there. The main strength, reliable, general, and cheap in the classical qubits, like in quantum qubits, massive data cachings, simulations, and big data. Unmatched for the certain classes of exponential problems in done in the quantum computers. So where we are using the this kind of a processor, when you go for the best application like in word processing and standard computations in the supercomputer, here, high processing we are using as weather modeling, climating, AI/ML training, and genomics will be done in HPC. Here, the factorization for the quantum computing, we have a short that is in factorizations. We have sessions like an global algorithms and quantum simulations and cryptography done with the help of quantum. So these are the like a major part which we can do the applications in that. Then error handling, well established on robots in supercomputer. standard error corrections and redundancy in the high HPC. We have the challenging and quantum errors corrections needed. Okay, so we have the quantum error corrections for calculating with the help of an like an like we have bit flip, phase flip, and we have bit and phase flip is done in the quantum error correction. Okay, position we can handle with the help of this three step. One is an bit flip, phase flip, and bit flip plus and phase flip. Okay. So these are comparisons of an three high-speed computing, like an quantum computing, high processing computing, and common software computing. Okay. Current limitations, like we have the reprograms, scalability, and usually stage of failure. So we are focusing the hardware. As I said, that hardware in the IBM, so what they are doing is to find the electrons. Okay, to find the electrons in the quantums, we had to cool down up to 200 above 273 Celsius in quantums to get that right. So there is a current limitations. Like a lot of research is going on this area of calculating finding the errors, okay, like an identification of an quantum bits. And integrations, we have integrated with an hybrid quantum HP platform. So, like quantum's integrated lot of technologies, okay, lot of emerging technologies, like what I showed in the first 50, like we are integrated with an AI, IoT, sensing, materials, and we have the some techniques of an quantum processor, okay, right? So we are going to see about quantum data structures. So why it is required for the quantum data structures? As a classical qubits, we know about how to store the data, how to retrieve the data in the with the help of data structures. As same as we have had to maintain in the form of an quantum qubits. So the quantum qubit data structures are designed for the store, access, manipulate the data encoded in their quantum state. That is how it can be done with the help of quantum parallelizations and probabilities access. So it is in backbone of a quantum algorithm providing a way of an organize and retrieve the data. Why classical structures rely on deterministic indexing, data structures which work on the superpositions of an indicates, enable the simulation operations for many elements. So here, what is the stage of an classical data structures? The inefficiencies with the superpositions, we have the arrays like, and we also have the arrays list hash table or digit in the form of an qubits. So like in zeros and ones, they cannot be represented or operate on the superposition state in the classical data structures, where the qubits can be simulated simultaneously hold their multiple values. Okay, so there is a main part of an quantum data, I mean, quantum data structures. Like complex quantum operations, we have algorithms operates on the entire the superpositions and entangled states, performing on parallel transformations. This is be done. So what is the part of this is we have lack of fault tolerance. There is a quantum states or error due to the decoherence, right? So this is a, some techniques you have to solve, right? The purpose of the data quantum data sets, efficient quantum states representations, memory access, implementing the quantum algorithm, and scalable data management. I like to show some data structures algorithm with the help of quantum. So I will show that quantum so advanced. Okay. So these are the things which is happening right now. Advanced quantum tree data structures. We have that from the starting of a quantum express tree, represent and manipulate the computational expression in the form of a quantum form. So how it started, like an leaves of a quantum operation, that is then we are making that quantum in the state of an quantum operand. Okay, like for example, calculating of an plus symbol, like traversal. Okay, we have in the traversal structure, we will be creating the quantum, I mean, data in the classical data structures. Likewise, we have the leaves and quantum operands like an qubit states and parameters in them. The internal nodes, we have the quantum gates or an unitary transformations in the expression tree. This one enables the symbolic representation of quantum circuits and the arithmetic operations done. So where we are using this expression tree, we will be using it in the form of quantum compilers, symbolic optimization, and the variational algorithm is used in this expression tree. Then we have a decision tree, like an machine learning algorithm. We have the decision tree, as similar like that we have in quantum data structure. Also, we have the quantum decision tree. The quantum versions of the classical decision tree for the reasoning or classification is done. The nodes are represented of quantum operations based on the features qubits. The leaves encodes a class label in the superpositions. The evaluations use the inference for the fast decision resolution is done. So where we are using this decision tree, we are using a quantum machine learning, pattern recognition, and decision tree, which is we will be using a quantum decision tree. Then we have the quantum decision forest, like in random forest, we have in the quantum decision forest. We'll be using often immeasurable learning and predictive modeling, and mostly we'll be using for the bioinformatics. The purpose of this in quantum enable for the immeasurable for of an decision tree. We have the concept like it combines the multiple entanglement quantum trees and enable the output combined with a quantum instance. Right? Again, we will go for the quantum tensor tree, that is we are calling as QTT, right? We are representing the form of for the hierarchical or an correlated quantums via tensor structure, right? As we have in like an TensorFlow or like an any kind of an machine learning concept, same concept can be used with the help of quantum TensorFlow. Each node in the form of tensor and the edges and its concentrations between the subsystems enables the compressions and the efficiency representation of high-dimensional data. We will be using for the application like in quantum chemistry, tensor network, simulation, and variational quantum solver. So, with the help of the tensor tree, we will be using the solver problems in the quantum chemistry and the tensor network simulation can be done. Then we have that quantum entanglement tree, encoded relationships like an using of an entangled modes and the quantum correlations. The concept where you are using this entanglement trees in the neural networks of quantum neural networks, relational AI communication protocols, we will be using of an entanglement tree. That node corresponded to the entanglement qubits group. Edges represent quantum correlations, not the data flow. Then we have the one important concept of an quantum walk the tree. So what is the purpose of the walk tree? Explore the tree using of superposition and interference. Where we are using this walk tree, we are using of an search algorithms, the networking and the optimization problems. Right? Enables the parallel explorations of paths. This is the main concept of an walk tree. Then we have the quantum search tree, the hierarchical data structures for the quantum search algorithms. So hierarchical data structure for a quantum search, we have an algorithm, we have a search tree. So what is the concept behind this of an Grover algorithm, which use the search tree will be used in this algorithm, and it uses the amplitude amplifications for the target node discovered. We have the quantum database search hierarchical decision problems will be solved. Right? Then we have that quantum probability key, which is used for the Bayesian networks, okay, and probability reasoning and uncertainty modeling. We will be using this probability key, like probability reasoning. For the uncertainty, we will be calculating the value in the AI concept, right? Model probability translations and measurements outcome will be done. The concept of this, we have each branch node. If possible quantum measurement path will be done, we will be using the probability and amplitude assigned for the or to the transaction. Then we have the traces tree, state tree, which is used for creating the solving the problem of an debugging and visualization, symbolic state propagations. Then we have that quantum. These are the like an tree structures in the classical qubits, right? Data structures we have that. Same way we are created that quantum for calculating that how we are storing the data, how we are retrieving the data. We have to use this kind of an classical qubits, right? uh, the principle of a quantum structure, right? As we have in classical qubits, like an linear data structure as a non-linear data structure, it will be also come under the form of an quantum state. We have that arrays list stack queue, right? So what you are seeing in the form of an like in different algorithms in the quantum state. So everything will be in the form of an superposition and the parallelism is calculated. It allows the operations like in search, insertion, or deletions using the quantum algorithm that leverage the superposition and parallelism is done. And then characteristics of an quantum linear structures, right? As well as we have the superposition, entanglement, linear arrangement. So this is the part where that data can be stored and accessed. Okay? Like and features elements maintained on an order that support the sequential operations like in classical linear structures. Like parallelisms, operations like search and comparisons can be performed on the all elements at once. Potential relation times complexity. So this is the linear structure data structure, and we will be going for the array. Then we have most important one is we will be using a quantum register, which is a quantum register as well as quantum random access like an classical qubits or foundation for the component in the quantum computing, serving the different interrelated roles in quantum data storage and processing. So, as similar to classical qubits, we have Q register in the quantum for retrieving the data and storing the, and processing the data, everything done with the help of an Q registers. So here the relations and goals. The Q register is required for computations and manipulation of quantum data. It's where quantum states lives and quantum logic gates are operated. We are using of an QRAM provides an efficient memory access machine mechanisms for those quantum registers which is used in the right, making the quantum data structure and algorithm practice all the states. Right? We have the quantum stack in the data structure which is similar to an live last custom, but operations like a fusion box will enhance in the form of an quantum superposition. Right? The Q is also there. We are using the form of algorithm called walk algorithms for the we'll be using an NQ and DQ operations done, and a single like an linked list we will be using in the form of an superposition and parallelism, right? We will be pointed with the help of an pointer to the next node, which can also represent a quantum state. So we will be represented in form of a quantum vector. That quantum vectors will be calculated in the form of an superposition and parallelism. Linear data structure, and we have the limitation of the decoherence measurement and complex implementations. What is the purpose of the quantum linear data structures? Will be for used for the speed up, parallelism, and the efficient storage is done. Where you are using this linear data structure, we will be using the form of an global search algorithms, quantum walk, and amplitude amplification calculations enhance the probabilities of measuring and desired state. Then we are focusing on non-linear directions. We have that three graph heap. What we are shown in the different algorithms we have similar like an classical qubits. It will be calculated in the form of traverse search or manipulate them faster than classical qubit method. But not connected in the more complex manner, but such as a tree or graph. Leverage the quantum properties like superposition, entanglement, and parallelism for efficient operations. Here, the three, what I have shown the three algorithms, similar, it will be calculated for the quantum tree. And we have the quantum graph, which is in the form of represented from register. Like we have heap in classical quantum classical data sets. Similar that we have quantum heap nodes stored as an quantum states. Superpositions can be find the maximum minimum elements faster using a quantum search techniques. So this is the techniques which is used in the non-linear data sets. So up to now, we have seen about how the data is stored and how the data set acts with the help of like in classical qubits. Uh, with the help of the data, only we can make the machine to learn. So we have the concept of quantum computing with the AI concepts. So recently, you know that AI we are using all over that like an machines. Likewise, we'll be integrate that AI concept with the quantums. Then will be useful for the predictions, and it will be solve the problems of an human beings, right? That is a quantum intelligence, the combining of an quantum computing with the AI concepts. Here the types of an quantum AI, which will be starting from quantum machine learning. We have the data input data and encode with qubits. The help of quantum circuits will be trained and inference and will go for the predictions. So likewise, we have the uh, machine learning concept, right? Here will be often encoded with the help of an state, okay, state to accelerate that ML task. Okay, with the help of the state and represented form of an zeros and ones, right? From the qubit state to from the qubit state to so here the encode will be done, which is represented in the form of an, this state to and like this, okay, like this or this will be converted the state. Okay, it will be encoded and quantum circuits. So with the help of an Harvard gate and Wizard gate, so they will be generated with the help of an unity gates. Then will be trained and inference and will be predicted. Next one we have that quantum inspired AI. So inspired computing. So like and the colony like we have like a lot of inspired computations brave to optimizations. Then we have a lot of optimization techniques like inspired computing. We have the classical hardware simulation principle done in the quantum principle and approximate optimization done. Then we have applied to the AI task. We'll get the output like this. So this is an apply for quantum like an algorithm on this classical stage. Now we are going to combine the quantum with a classical AI. We have to start from the classical processing, send heavy task to the quantum processing unit. Then we'll be doing a parallel computations in the quantum processing unit. Then we'll be merge the result with the help of a CPU. Then we'll get the output. Okay, this process we are calling as quantum hybrid quantum classical AI. Then we'll go for the optimization techniques for solving the huge optimization problem for the faster. Then here we have that optimization problem. For example, if we have to solve the problem from classical optimization, we are getting a limited number of occurrences or any kind of problem in the classical. We can go for the big encode into an quantum state. We will be applying the quantum tunneling. What will happen is we will be process the data to make that into increase your accuracy in the form of an activation functions and with the help of an quantum tunneling. We will be explore the solutions here and we will get the outcome. Okay? So this process of an quantum optimization. Then we have the quantum natural language processing. We have the input languages. We have all kind of languages like our country. We have different types of languages. Will be encoded into a quantum state. Then with the help of quantum circuits, will be converted to semantic reasoning. Finally, we get that natural language output. So this type we are calling as quantum AI. Like a definition of quantum AI, it is an intersection of quantum computing and artificial intelligence. The main how will be converted information superposition, entanglement, and interference. to enhance AI algorithms. So practically for a task that computation is expensive for the classical computing. Here the solve of what is the goal of this is solve AI problem faster and more efficiently than classical AI. Okay. So for example, if I have classical AI content have 1 terabyte of data, so to make the model, it will take more time to computation power, right? It will take more time to take for create the model. But in the quantum AI, will be solved with the help of a faster and more efficiently than the classical AI. Surely we have some noises. Okay, we have some noises that creating a model. For this model creations, we can use some optimization techniques, or we have different techniques that focus areas on the machine learning concepts, optimizations, neural networks, and data analysis. Right? Why quantum AI? Why we are going for quantum AI? The classical AI has a limitation due to a large data sets, complex models like deep learnings and transformers, optimization problems like training and feature selections. So these are some limitations in the quantum AI. Sorry, the classical AI. In quantum computing, we have some parallelisms and superpositions which can be done simultaneously. We can go for the for solving the more complex models, and the optimization problems can be then solved. Then entanglement, encode complex correlations in data efficiently. Then we have that quantum speed is also there for reducing the time complexity for the certain AI task, like searching, optimizations, and pattern recognition. So that's why you're going for quantum AI. In the application of quantum AI, we'll be using for that like machine learning concepts. We have the support vector machine learnings for the faster classification, neural networks like quantum neural networks for enhanced learnings using quantum layers, quantum clusterings like we have the efficient dimensional reductions already done. Optimizations, AI models often requires the optimization for often loss functions and hyperparameters. That quantum algorithm like QAOA, where you can right? Quantum approximate optimization algorithms can be solved like an optimization problems faster than the classical method. Okay? We'll go for that natural language processing from encode of high dimensional words like embedding the efficiently using quantum state, enable the faster semantic similarity computations done in the natural language processing, like finding the tokenizations, finding the semantic, everything will be done with the help of an quantum state. One more application will be drug discovery and material science. AI model predict the molecular interactions, like for identification of DNA. Okay, for identification of DNA similarities, similarities can be done with the help of a drug discovery. For example, if you want to find a drug for the new viruses, this can be quantum computing can be used to identify that drug discovery. Okay? With the help of the parallel and simultaneous work, we can solve the problems of the identification of drug. Okay, AI model predict the molecular interactions. Quantum AI allows the simulation of quantum systems molecules directly, improving the prediction accuracy. We have that quantum algorithm for AI, like in Grover, which is for the Grover algorithm for the data search, and benefit of this order of root time. So speed up, we will be using of Grover search. We will be using of quantum Fourier transform for the signal processing, efficiency and feature extraction is done. Pure for the optimization for AI applications. Faster coverages for training and feature selections is done with the help of Pure. Variational quantum circuits, we have that QNN and the efficient chain for the QNN. So these are the algorithms which can be implemented with the help of the can create that model with the help of the AI concept. Machine learning concepts, as we are discussed in that support vector machines, K means clustering and quantum QR. PCA algorithms, which is for the faster processing of high-dimensional datasets and input feature extractions. Likewise, we have the generative AI concepts for the model. We can create a model like a GAN. Okay, we have that quantum GAN, and quantum resolution auto encode will be done. Right. So how it can be done? It is like we have encode and decode the GAN. We'll be creating a generating the image with the help of a quantum is also possible nowadays. We can generate the data. We can use for the generating that images, right? How the real classical AI is generating like that, we have that in the form of a quantum also generating. It will be useful for the drug discovery, like generate the new molecules, and we can go for an art, music, and image generations in the generative AI format. So synthetic data for training classical AI is done. This is like now we are focusing on the IoT concepts. In IoT concepts, like in real-time IoT, we have the devices, right? If suppose if any problem occurs in the environment, I have to transfer the data to the cloud. Then I will receive the data, okay, to the mobile phone. Likewise, we have the quantum sensing, right? We have the quantum sensing. With the help of the quantum sensing, I can transfer the data to the communication part to make that to make it a form of an IoT devices, right? Quantum IoT is an integration of quantum computing with IoT devices. It is an quantum technologies to enhance the IoT networks in terms of security, data processing, and efficiency. Right? And quantum IoTs combines that to handle the massive IoT data with a high security and fast analytics. Here we have the IoT features of enhanced securities, like we are using of quantum key distributions, ensure that unbreakable encryptions for the IoT communications done. Likewise, we have that blockchain concepts in that part. We are securing that uh, data in the form of a blockchain. We have that quantum blockchain also concept is used. Okay. Faster data processing. We have the large data in at a parallel. Okay. So why we are going for quantum? We can do large IoT data sets in the parallel. The efficient resource management. We are using of an optimization improves the energy consumption and routing in IoT networks. Then scalability, how that million of data can be transferred with the help of the quantum. So quantum resources allows the handling of billions of IoT devices without a classical bottleneck, right? So this will be an upcoming years. We have seen a lot of quantum will be involved in for transmitting and controlling the IO devices, right? We have the architecture of the quantum. So start from the processing, communication layers, and we have the application like layers. So where we are using this IoT in quantum IoT, we will be using upon smart cities, healthcare IoTs, autonomous vehicles, and industrial IoTs, and grid. Okay, everything will be controlled with the help of an quantum part. Benefit of an IoT challenges, then cloud. Okay. Actually, I like to show some real-time part. I will show that quantum concept in that. Okay. I have done the project in the form of an UA format. So you can see that I'll start from the. Okay. I have created matrix calculation. Here I started from the state vectors. I have done this for addition, subtractions, and multiplications operations. Okay. You can see here that project like a matrix multiplication is done. You can see that library files, quantum AER, matplotlib, and iGadgets. Yes, iGadgets. You can see that. Okay. Imagine that this is a matrix of 1001 and matrix A and matrix B. The operation is done with the help of an addition, subtraction, multiplication, tensor, and conjugate transpose. Well, these are the operations can be done. So let us check with an addition when we are using as addition. If you compute these additions, you can see that vectors, state vectors is calculated. So suppose if you want to see about it in form of an quantum sectors, okay, so it will be displayed in the structures, right? Likewise, you can see in the format of okay, like let us show in this in different angle of an matrix multiplications and matrix additions. Yeah. So I have taken in the form of a 3-qubit state, like a matrix A and matrix B. When we giving in the form of states, when we compute this one, we are getting this state, right? When we go for this, okay, like and we have to go for 2 states. So when you come prepare this, you can see. Okay, actually, it will create one sphere structure, but it is computing with the help of an vector state. Okay. So likewise, we have that in the form of an a million number of an matrix will be calculated. Suppose if you go for matrix multiplications, you can see that vectors calculated. Again, that we have that Bell state. Okay, Bell calculations. For Bell state, we can see when we're going for compiling this code, you can see the noises. You can generate the if you're applying the noises, it will be calculated. Here, the visualization part of an state evaluation simulator part. Here, that state vectors can be calculated of an dimensions. Okay. Here, I will show how it is. Okay. Uh, here. Okay. Suppose if you want to learn about the matrix, I mean gate. Okay, I have created one simple part. Here, what is happened here is when we are giving it in the form of an single qubits, we have 2 qubits here. Okay, I'm going for a single qubits. The initial state is zero gates, 1 gate, and plus gate minus gate. If I'm giving for 1 gate, I'm applying an X gate here. You can see that initial state, which is in the form of an 0 gate. When I applying the X gate, it will be in the form of 1. Then we'll get the state of final vectors, and we can measure the probabilities here, and it will be automatically create the circuit. Okay. Likewise, we can give Z gate. When we run this gate, we can see that this is an initial gate, initial state. It will be go to the if you are applying that 0 qubits. So initial, I mean after the applying the Z gate, it will be in position like this. You can see that part. Now I'm going to show that in the form of a 2-qubit state, that is an entanglement state. When we're going for the Bell state of this, when we are applying this run state, you can see the plus qubits, plus gate. Okay, so you can see that circuit is generated, and you can see the measurement of that part, and you can see the box sphere which is applied here. Okay. Okay. When we go for this my gate, okay, you can see that gate is already created directly here. Hudband gate and X gate is applied into an C not gate. Okay. We will be getting the values like this, right? Likewise, we have that gates is generated in this coding part, right? Um, so these are the form of like I will go with some techniques of an cloud access. In the cloud access, it will start from that QAS, that is a software as a service. We have that Amazon brackets, like we have Amazon brackets, Microsoft have Azure Quantum, Google have Quantum AI, and IBM have that IBM Quantum software the platforms. Provide the developers we can do develop research and business with an on-demand access to the real quantum processor. We have that cost efficiency and the accessibility in that quantum access, cloud access. Okay, so these are the concepts which we can cover, like, and we have working on that IBM quantum, right? right? This is a comparison between the each and every providers, right? IBM, Amazon, Microsoft, and Quantum, and we have the Quantum Ring SDK. So platforms and quantum technologies which is used in that part. IBM, which is used in superconductive, qubits. Amazon, we have that multiple backends. So in Microsoft, we have that name called QTIS. Okay, QTIS, we have the QTIS in that Microsoft. That is also an quantum, which is used for the hybrid classical and quantum states. It is an we can learn from the Microsoft website. That is we will be calling as QTIS, right? In Google, we have that quantum AI cloud, and it is used for the calculations. And quantum ring, we have open quantum cloud up to 100 qubits will be calculated. So these are the major QAS providers. Finally, we have this quantum sustainability. As you know that we have a lot of goals in that format. Quantum will be included in the sustainability to calculate. Okay. The core idea behind is traditional computing struggling with a high complex simulations and computation needs for the sustainable. In quantum computing, which will have the superposition entanglements and can analyze the massive and interconnected systems, so much faster and more accurately it will be used. So how it is calculated means, I mean, how it is used means, with the help of an quantum sustainability and quantum intelligence, we will be using of an quantum innovations then. These are the some domains where the quantum can be used and it is the impact is done. Okay. We have that energy system, climate modeling, material science, agriculture, supply chain. We have the algorithm. Okay, we have some techniques to calculate that process. Right, and waste management is done with the help of IoT devices. Supply chain we will be using of logic. Okay. So agriculture, ML for crop yield, and material science we have the chemistry discovering new ecosystem. So these are the some advantages. Okay.
I think participant, please mute your mic.
Okay. So with the help of sustainability, we'll be solving the problem for that AI concepts where that AI can be solve the problem of human beings, right? AI plus quantum for the sustainability, we have that agriculture state and energy forecasting and one climatic model. IoT devices, we'll be using of an water quality monitoring and forest fire detections and waste management system can be identified with the help of an quantum IoT. And we will be using of an cloud where automatically we are using as edge AI as well as an agentic AI. In that part, quantum will be included to solve the problem for the human beings, right? For the cloud, for the sustainability. Finally, we have some case study of research, IBM quantum, and we'll be using for the battery in the chemistry. Okay? For electric vehicles, we'll be using a quantum. Right? We'll go for the quantum simulations. Will be done with the help of this. Okay? In Google Quantum AI, we will be focused on the climatic simulation to predict the atmospheric reactions for the CO2 and the interactions. And the quantum ring SDK projects, we have the quantum optimization for smart farming and waste management. In that Microsoft Azure, we'll be focusing on that energy efficient hardware and the carbon negative components done in the help of this. So here we have the future vision as we are discussing about an sensor and simulators, AI, ML models, and blockchain cloud collaborations. So for the environment and we will be focusing about the human take care, right? Human problems solving techniques, right? So that's all. Thank you, ma'am, for the listening. Hope I have covered from AI to sustainable, right? From basics to sustainable. Here, a lot of things is going on right now. There is a lot of projects with me I like to show, but can discuss later.
Okay. Thank you, Dr. Kumar. I think a very brief and very simple presentation. And I think if somebody goes to a presentation, you have explained the basics and also advanced topic of quantum mechanics in a very, I think every point, I believe every point you must have covered. Thank you for that, sir. It's a very wonderful presentation. I think little bit voice is not very clear. Sometimes it is just going here and there. Otherwise, it's very good, sir. Participant, if you have any question and query, you can ask, or you are put in a chat box. And one thing, sir, I have one query, like if you can put your slide or some notes you can provide so that participant can learn about some book links if you can provide to the participant.
Okay, ma'am. Sure, ma'am. Shall I share to you, ma'am? You want that notes to you?
Yes, sir.
You need the notes to you, ma'am. Shall I share
Yes. These PDF, PPT, if you can provide, then I can share with the participant.
Sure.
I think because people for learning purpose, they are very good. Excellent.
Yes, ma'am. Yes, ma'am.
Okay. So participant, if you have any question, then please let me know. I think there is a lot of, material to learn, right? So mostly people are trying to learn what they are saying here. So now I will request Mr. Devanshu to present us a certificate of appreciation to sir. Thank you so much, sir.
Thank you, ma'am. Thanks for this opportunity. Actually, I like to show some demos for the quantum plus AI concepts. I feel that I like to share some basic concepts of quantum, then I can do it. So thanks for this, man.
Okay. So we deeply appreciate your dedication in sharing your knowledge, expertise, and insight on the topic Introduction to Quantum Computing from Basic to Advanced Concept. Thank you very much, sir. And I hope we will see you soon again in some other workshop.
Okay, man. Thanks
Thank you so much, sir.
Thank you.
Okay. Thank you so much. Okay, participant, I have one announcement, because since we are moving towards our closing session, which is tomorrow. So tomorrow we are going to start our session from 4 p.m. Okay, so tomorrow we have a one lecture, which is from 4 p.m. So after that, we have a valedictory session. So I will keep this updated on WhatsApp group, but this is for information. Tomorrow we have a session from 4 to p.m. Okay, after that, we have a valedictory sessions. Okay, thank you very much, everyone. Thank you very much. Now, all you can leave the meeting. Let us meet tomorrow, 4 to p.m., 5 to p.m. Okay, thank you.